Hi guys, in the last lecture we covered two of the three-phase transformer connections. First one that we saw was star-star connection. In star-star connection we saw there are two type of phase shifts possible, that is 0 degree and 180 degree. For 0 degree we called the connection as YY12 and for 180 degree it was called as YY6. The only problem with the star-star connection was the production of third harmonics in the flux and the EMF. And to remove those third harmonics, what we did was we used a star with a grounded neutral, or we connected a delta connected tertiary winding in between primary and secondary winding. Delta connected winding allows the flow of third harmonic magnetizing current, due to which the flux will become sinusoidal, and if flux is sinusoidal, the EMF will also be sinusoidal. So that way we can make the EMF sinusoidal in case of star-star connection. The problem with the third harmonic was that third harmonic causes the floating neutral, due to which single phase load could not be connected across a star-star transformer because the neutral was oscillating or floating. Then we covered the delta star connection. In case of delta star connection we saw there were four phase shifts possible: plus minus 30 degree and plus minus 150 degrees. And we saw that VL secondary by VL primary was root 3 into NS by NP. So it has the highest secondary voltage as compared to star-star or delta-delta connections, hence it must be used as a step-up transformer. And also due to delta connected primary winding, it allows the flow of third harmonic magnetizing current, due to which EMF and flux are sinusoidal. So that was the advantage with the delta star transformer. In this lecture what we will be doing is we will be covering rest of the three-phase transformer connections to complete this three-phase transformer. So let us first start with star-delta transformer. The procedure to draw the phasor diagram remains the same. First we will draw the primary phasor, and based on that we will draw the secondary phasor. Primary phasor must be drawn keeping in mind that this phase should be vertical. So let us draw primary phasor first. This will be A1 to A2. Then A1 is connected to B1. This will be B1 to B2, 120 degree lagging. Then B1 is connected to C1. This will be C1, C2, again 120 degree lagging. This will be my neutral point. Now let us draw the secondary phasor. This will be my A1 to A2. Now if you see, A1 is connected to B2, this one. So A1 will be connected to B2, it will be like this. This will be B1. Now B1 is connected to C2, so it will be like this. This will be C2, this will be C1. Now we know that the output is taken across A2, B2 and C2, so we must remove the subscript 1 terminals, that is B1, A1 and C1. So to find out the phase shift we will have to draw the reference phasor in delta. This will be my reference phasor. This will be A, B, C. Now if we plot on a clock, capital A is like this and small a is like this. So here we find that a phase shift of 30 degree clockwise, that is 30 degree lag. So it will be called as YD1 connection, because in the clock it appears like 1 o'clock is the time. So it will be my YD1 connection. Okay. Now let us change the primary connection and try to determine the phase shift of the transformer. So here what I have done is I have connected A2, B2 and C2 to the neutral. So if we draw, let me draw like this. This will be A2 to A1. This will be B2 to B1. This will be C2 to C1. This is my neutral connection. Okay, now secondary phasors will be drawn in parallel with the primary phasor. So we have to draw A1 to A2. A1 to A2 will be vertically downwards, because A2 to A1 is upward. So A1 to A2 will be vertically downwards. Now A1 is connected to B2. So we have to draw B1 to B2. B1 to B2 will be like this. This will be B2. This will be B1. And then B1 is connected to C2. So C1 to C2 will be like this. This will be C1. Now we know output is taken at A2, B2 and C2. So we must remove the 1 subscript terminals. So this we must remove. Now to find the phase shift, we must draw the reference phasor. This will be A, B, C. So on a clock, if we see, capital A phase is like this, small a is like this. So this will be YD7 because it appears like 7 o'clock is the time. And if we see, the phase shift is 150 degree anti-clockwise. So it is 150 degree lead. 150 degree anti-clockwise phase shift, that is 150 degree leading. Okay. So that is how you must determine the phase shift in any transformer. Let us change the secondary connection now. So first of all, we will draw primary phasor. Primary phasor will be drawn similarly. This will be A2, A1, B2, B1, C2, C1. This will be my neutral point. Now to draw the secondary phasor we will draw. First, if we need to draw, we are taking the output at A2, B2 and C2. So let us draw A1 to A2. A1 to A2 will be vertically downwards. A1 to A2. Now A2 is connected to B1. So B1 to B2, how it will be? B1 to B2 will be like this. Now B2 is connected to C1. C1 to C2 will be like this. Now since we are taking output at A2, B2 and C2, we must remove the 1 subscripts. Now we will need to draw the reference phasor. Okay. This is A, B, C. If we plot on a clock, capital A is like this, small a is like this. So this connection will be YD5. Okay, because it appears as if 5 o'clock is the time, so it will be YD5 type of connection. Now again let us change the primary connections. Now primary is like this. So first let us draw the primary phasor. This will be A2, B2 and C2. This will be A1, B1, C1 and neutral. If we draw secondary phasor, A1 to A2 will be like this. A1 up to A2. Now A2 is connected to B1. So B1 to B2 will be like this. Now B2 is connected to C1. C1 to C2 will be like this. Okay. Now we will remove the 1 subscripts. Now we will draw the reference phasors. This will be A, B, C. Okay. Now if we plot on a clock, capital A is like this, small a is like this. So if we name the connection, it will be YD11. Okay. That is, we are getting a 30 degree anti-clockwise shift. So it is 30 degree leading. So it provides a phase shift of 30 degree leading. So if you observe, the star delta transformer provides a similar type of phase shift as a delta star transformer. That is, we have seen 4 type of phase shift: plus minus 30 degree and plus minus 150 degrees. Okay. So that similar type of phase shift is obtained with star delta and delta star. Now let us see some of the features of the star delta type of transformer. First of all, if we find out ratio of line voltages, VL secondary by VL primary. Now secondary side is delta connected, so it will be V phase secondary, but primary side is star connected, so it will be root 3 V phase primary. So it will be 1 by root 3 into NS by NP. 1 by root 3 will be 0.577 NS by NP. In star star and delta delta, we saw that line to line voltage ratio was same as turns ratio, but here it is 0.577 times turns ratio. That is, I can write it like this: NS by NP minus 0.423 NS by NP. That is, it is 42.3% less as compared to star star or delta delta transformer. That is, in a star delta transformer, the secondary voltage is lesser as compared to star star or delta delta type of transformer. Since secondary voltage is less, it can be used as a step down type of transformer. Okay, it can be used to step down the voltage or reduce the voltage. Since voltage is getting reduced, if you want to keep the voltage same, you have to increase the number of turns. That is, for the same voltage rating as a star star or a delta delta type of transformer, star delta will require more number of turns. Okay, so here to keep voltage rating same, number of turns will increase. It requires more number of turns as compared to other connections. And the last thing is that since the secondary is delta connected, so delta winding will allow the flow of third harmonic magnetizing current, due to which EMF and flux will be sinusoidal. Remember, whenever there is a delta connected winding, either primary, secondary or tertiary, it will always keep the EMF sinusoidal. So ideal case is that either one of the windings should be delta connected. In any transformer connection, one of the windings, if it is delta, it will allow the flow of third harmonic magnetizing current. So that is the features of the star delta type of transformer. Let's look at our last connection for the three phase transformer, that is called as open delta. So here I have shown a delta delta connected transformer, and we know the power rating of delta delta connected will be, or three phase will be, root 3 VLIL, or we can say 3 V phase I phase. Okay. Now we define something called as transformer utilization factor, TUF. Transformer utilization factor. It is nothing but power output by 3 into, or let us say not 3, number of transformer N is the number of transformers or number of single phase transformer into rating of one phase. Okay. Since we can consider a three phase transformer as consisting of three single phase transformer, so in this case N will be 3. If there were two transformers, I will consider N as 2. If there is a single phase transformer, N will be taken as 1. Now power output is 3 into V phase into I phase. Number of transformers are 3. Rating of single phase transformer would be V phase into I phase. So this transformer utilization factor is 100%. That is, I am utilizing the capability of the transformer completely. I am not wasting any of the capacity of the transformer. 3 transformer can combinedly give me a power of 3 V phase I phase. That is the power that I am using. I am not wasting any capability or the capacity of any of the transformer. Now sometimes what may happen is, since a 3-phase transformer is assumed to be consisting of 3 single-phase transformer, due to some fault or due to some malfunctioning, one of the transformers may go off. So we may need to disconnect that transformer. Then this connection will be called as open delta type of transformer. Okay. Suppose this phase develops a fault and we need to remove this phase. Then this will look something like this. Okay. That is called as open delta, or it is also called as VV connection. Because on primary and secondary side, if you see, the shape resembles a inverted V. So it will be called as VV connection or open delta connection of the transformer. So if we see here, VAB is applied, I current is going, which is being divided into two paths, IAC and IAB. So let us try to draw the phasors. First let me take line voltages as reference phasor, VAB, VBC and VCA. Now the current IAB, it will be in same phase as VAB. I am assuming a resistive load, so it will be IAB. Then IAC will be in the same phase as VAC. VAC will be opposite to VCA, so this will be IAC. Sum of these two currents will give me current I. Okay, these two currents are oriented at 60 degree to each other, so this I will be root 3 I phase. By vector addition, if you determine by parallelogram law, it will come out to be root 3 into I phase. So rating of the transformer would be root 3 into V phase into I phase. Okay, because current is I phase, voltage is V phase. Sorry, current is root 3 I phase, voltage is V phase, so power will be root 3 V phase into I phase. Now if we try to determine the transformer utilization factor TUF, then here we have two single phase transformer. So maximum capacity is 2 V phase into I phase. Actual power drawn is root 3 V phase I phase, but capacity due to two transformers is 2 V phase into I phase. So it will be root 3 by 2, that is how much it will be, 0.866, that is 86.6%, which implies that I am only using 86.6% of the transformer capacity and not the total capacity of the transformer. That is, I am wasting 13.4% capability of the transformer. That much additional power I can draw, but I am not drawing in this connection. Now let us see what is the ratio of delta delta and the open delta connection. So KVA rating of a VV type of connection or open delta divided by KVA rating of delta, it is root 3 into V phase into I phase, but it is 3 V phase I phase. So it is 0.577 or 57.7%. That is, if you disconnect one phase of the delta delta type of connection, still your transformer is not inoperational, but rather it delivers lesser power. It can deliver 57.7% of the power. You need not shut down the entire transformer in case one phase develops a fault. We can operate the transformer at a reduced capacity. How much is it reduced? 42.3% it is reduced. So remaining power is 57.7%. And the KVA handled by one transformer would be root 3 by 2 into V phase into I phase. Both transformer will develop same power, or the power will be divided equally. So it is 0.866 V phase into I phase. Okay. So that is how much power is delivered by each transformer when we are taking two transformers in a open delta type of connection. Okay. But if you need to deliver the same power as the delta delta connection, so how much current we will require? I am saying we need to deliver the same power as the delta delta type of connection. It implies I phase dash will be root 3 I phase, that is I phase dash will be 1.73 times I phase. So it is 73% more as compared to delta delta type of connection. So if you are supplying the same load as the delta delta connection, that then you have to draw 73% more current from the source as compared to delta delta connection, due to which each transformer will be loaded with an additional current of 73%. Okay, you have to draw 73% current extra, due to which the windings may get overheated and damaged. So that is a dangerous thing if you want to supply the same load as the delta-delta transformer. So let us summarize what we have learnt in this lecture. First we saw star delta type of connection, in which we saw there were 4 phase shifts possible, plus minus 30 degree and plus minus 150 degree. And we saw that the secondary voltage is least, so it can be used as a step down type of transformer. And since secondary winding is delta connected, it allows the flow of third harmonic magnetizing currents. So the secondary voltage or EMF will be sinusoidal. And last we saw open delta type of connection, in which we removed one of the phase of the transformer. Then the kVA rating was √3 V phase into I phase, which is 57.7% as the delta-delta connection. So it is a reduced capacity. So if one transformer develops a fault, no need to shut down the entire bank. You can use 2 of the 3 transformers and produce a load which is lesser than actual load, but still power is non-zero. No need to shut it down. So this is all about the 3-phase transformers that are covered in the GATE course. Though there are many more connections, but those are not in the GATE scope. Like zigzag transformers, those are not covered in GATE course. So even if you read them through a book, no need to go through those, because that will only cloud your mind and that will not be helpful in your GATE examination. So this is all about the 3-phase transformers.